So now we're focusing on a slightly more general case where the addends are any number of numbers and the weights are still unity. In this case, it turns out that you can transform the problem with addends into a problem without addends. Okay? You can do that. How do you do that? Let's pick, for example, addends. Let me just put down the weights here. The edge lengths 5, 5, 6, 3, 2, 2. John, was this 3?
Yes.
3? Okay. So suppose A1 is 2, A2 is 1, A3 is 1, A4 is 5, A5 is 1, A6 0, A7 0. Let's assume that this is the situation. Okay? Now, what am I trying to do? I'm trying to find z and a point x such that the distance x to vi plus ai is less or equal z. That's what I'm trying to do. Now, if I happen to pick, for example, the midpoint again, as in the previous case, then what would be the largest distance plus addend value for this point? In other words, what would be the f value if the point under consideration is, let's make it x cap, is x cap, right in the middle of this edge. Okay? In that case, it would be the maximum of a bunch of numbers. The first one is 3, 6, plus 2 is 8, plus 2 is 10. The second one would be how much? 9. What's the third one? 9 plus 1 is 10. Sorry, 3 to 6, 7. This one, 3, 5, 8, 13. Next one is 9, 3, 8, 9. Where am I now? This is the next one, that's 3. And the next one is 3 again.
I guess we missed.
Which one?
Assign weight to one of the nodes, like just between the A1 and A2.
This one?
A1 and
Oh, that one.
Yeah.
Let's make it A8. And let's make it 0. For the sake of simplicity. So that would be 3 plus 3. That's 6. Okay. So the maximum is 13. And the question is, well, is that the best I can do? What do you think, Özgür? Was it Özgür? Barış. Soyadın mı öyle? Ha? Okay, whatever. Barış. What do you think? Can I do better than that?
possibly yes.
Yes, possibly, of course. Possibly, yes. Well, who defines, or which vertex defines the largest? It's this one. So what do you want to do? You want to move closer to it. For example, just for the sake of argument, if I move, say, 1 unit to the left, then this would decrease the value from 13 to 12. Would it increase anything
Yes.
to
To 11.
how much?
It will be 11.
11. That, so there's still more room. So I can still further move how much? 0.5 more. So a total of, so we're talking about a second point here, x bar, for which the distance between x cap and x bar is 1.5. I don't know if you can see that, but that's a little 1.5 there, okay? So in that case, the value of f of x bar would be, it's reduced by 1.5, so it will be 11.5. Okay, you can compute that. So, of course, by inspection we can solve it like this. And the other way, the other way to solve this is simply to transform this into a new problem. I'm going to erase this now. In the following way. I simply add new vertices. So this one was vertex V1 before. Now this will be V1 prime, for example. It's a twin or it's a replica of that particular vertex. I just assign the length 2 here because A1 was 2 before, right? I erased it. I forgot. Was it 2?
Yes.
Yes, it was 2. So for this one, I'm just going to create this vertex V2 prime and assign the value 1 to it. So there's no more addend. Likewise, this one I don't have to do anything. That one, you create that. The next one, this is the long one. V5 prime with a length of 5 here. This one with a length of 1. This is 4, sorry. That's going to be V4. This is V5 prime. V6 prime, you don't have to do it. V7. So whenever the addends are 0, you don't have to create a new vertex. So in this problem, I happen to make the new edges dotted or broken lines because I cannot place a new facility at one of those edges. Okay? They are not allowed. So what happens is, in this case, if you just solve the longest path problem in this tree network, or the, if you just happen to focus on finding a longest path in the new network, this is the expanded network. Call it T prime, for example. Okay. The longest path in this case will be 5 plus 5, that's 10, plus 6 is 16, 19. I don't know which one did it. Yeah, I guess we go that way. 19, 21, 23. And your best value is half of that, 11.5. Of course, the expansion idea where you add a new vertex next to each old vertex and you connect the two vertices under consideration by a new edge whose length is whatever the addend was for the old vertex. That works not only for tree networks but for any network. So if you had a cyclic network with 3 vertices and addends of, for example, 1 unit here, 2 units here, 5 units here, it would work also in such a case. You would still be transforming this problem into a problem without addends, except that the number of vertices is twice as much at the worst case. Okay? And also, there's one anomaly here you should notice. If this addend were 25 rather than 5, for example, in that case, the longest path would be how much? Well, it's increased by 20 more, so that would be 43, okay, in this case. Longest path length in this new situation, the old one was 5, is equal to 43. And half of that will give you how much? That's going to be 21 and a half. Which means that I'm going to find the midpoint of that path. If that happens, if the midpoint happens to be on the solid portion of the tree, I'm fine. I can place it there. If not, in this case, it will not be. See, when you move from here, 21 and a half units, you go somewhere here. That's what you want to have. But since that's not allowed, what is your best next choice? This one. Okay? I guess the idea is quite straightforward. You can just see in your head that this is what's happening. Okay? All right.
But
Yes.
about the middle nodes, about their RSV,
Which one? These?
yes.
I just happened to pick them 0, but if they were not 0, you would just add whatever the addend is. For example, if the addend is 2, this was what? V6. So that would be your V6 prime here. Okay? Is that what you're asking?
Yes.
Okay. All right. So,
for example, nearest hospital to network vertex. In fact, in this case, when we insert this V5 for example, the network does not need to be a tree anymore.
true, but I'm not thinking of it this. This is a mathematical transformation. You're thinking of the physical situation. In the physical situation, of course, there could be a hospital here, and the distance here would be 2, the distance here would be 1, etc. That one is 0. I don't know why. Well, they don't use it, that one. There's another sağlık ocağı here, okay, little hospital. They use that one, but the other ones, they use that one, for example. Whatever, you got the idea. So when you start connecting this to all the vertices, then of course you have a cyclic network, but that's not what we're trying to solve, because I'm not interested in placing a location or a facility in the red arcs, okay? It's just in our head. So actually, this actually illustrates one thing. When you have data which is relevant to the problem, but if you're not, for example, able to place things in those new, in these red arcs, then you don't have to include them there. See, a lot of people make the mistake of, as soon as they start analyzing a problem, they don't think about these things, and they analyze it in such a way that it is very complicated. They may make it very complicated. Whereas if you're able to remove certain parts of the data for pre-processing or post-processing or do whatever, isolated from the actual problem on hand, and make the problem structure simpler, you do it. This is one small example of that, actually. Okay? Unfortunately, that's the art of modeling. Not everybody, it's very hard to teach that. You can't teach it. You just have to be conscious of that. You know, come up with the simplest model, you can. But how do you teach that? I have no idea. It's difficult. Some people do it well, some people don't. It doesn't matter if you are a practitioner for 40 years. You may still be doing things in a very complicated way. Actually, many people do things in complicated ways. Okay? All right. So let's look at the general case now. In this case, our problem is to minimize z subject to wi dx vi less than or, sorry, plus ai is less than or equal to z. For x being in the tree. Now, when you look at the constraints here, I prefer to write them in the following way. Subtract from z the addend and divide it by the positive weight. So this problem is equivalent to that problem. Minimize over z, minimize z over x in t, subject to distance constraints of this kind. Now, if z is a fixed number, if you just temporarily fix it, what do you want? Then for fixed z, that would define a certain radius, ri, which depends on the index under consideration, the index I. So you would like your point to be within a distance of vi. How much? Ri units of distance of vi. Okay, that's the idea. So let's define the subtree Ti of z to be the set of points in the tree network such that the distance between x and vi is less or equal that number. And I want to find the smallest z, call it, say, z bar, such that the intersection of Ti of z values is non-empty, has at least one point in it. Okay. Now, I know what I want. I want the smallest value of z such that these subtrees defined relative to a z intersect. I'm going to change it to a slightly different form and do the following. Given the numbers, well, the positive number, non-negative numbers, given the non-negative numbers Ri, I1 up to n, these are the radii you want to use. Find a point x in T, if it exists, such that the distance between x and di is less than or equal to Ri for all I under consideration. Okay? What's the difference between this and that? The only difference is I'm working with fixed numbers, with fixed radii here, whereas over there I'm trying to minimize something where it's just too complicated there. Right now, just focus on a simpler problem. If you handle the simpler problem for fixed radii, then you will know what to do there. Okay, that's the way to go about these things. Make it simpler and simpler. And at the point you get the simplest problem, if you're able to solve the simplest problem, then you move back and then make it more complicated later. People don't do it. I mean, I know I see the smiles in your faces sometimes, but people don't do these things. They just take the most complicated problem with the face value and they just dive into it. I have no idea why they do it. You cannot get out of it. Then they end up with heuristics. No, you want to analyze it first. Okay? All right, so this is a simpler problem. And define the neighborhood around Vi of radius Ri to be the set of points x in T such that the distance of x and Vi is within the radius. It's the same as Ti. Except that I'm going to give it a different name because that's the traditional way this was called in the literature. The neighborhood around the point Vi with radius Ri. It's the set of points in the network, in the tree. Of course, you can define it also for tree networks. Actually, maybe. Okay, yeah, anyway, that's it. Now I'm going to make it even more simple. Let's assume my tree consists of only a single edge. That's the simplest you can be. Well, there's one more level of simplest. You can have only a single vertex, but then you can't do anything with it. So you've got two vertices, V1 and V2. you have R1 and R2. Now, R1 says you want to move R1 units of distance this way. That gives you a neighborhood. That's my N1, N of V1 of R1. Okay, this portion. The other one is similar. Tells you to go R2 units. So maybe I should just do it this way. This one is R1, and this one is R2. Okay? Now, do they intersect? They do. In fact, any point along here is going to be a solution. That's the intersection. Okay? Let's take a simple case, again, with vertices V1 and V2. This time, that's my R1. And that's my R2. Now they don't intersect. So, what determines whether or not you have an intersection here? I'm not doing anything with z values right now. I'm working with fixed radii. Okay? Forget the z's. Just erase that. Length of the arc.
It is greater than the sum of the radii, and we don't have any.
So we're talking about the distance between V1 and V2. If it's greater than R1 plus R2. So if this is true, there's no intersection. And if it's less or equal R1 plus R2, there is an intersection. That's what you say. There's an intersection, means there's a non-empty intersection. Okay? Does it go the other way around also? If there is no intersection, would this be definitely true? Yeah. And if there's a non-empty intersection, then that would also be true. Okay. A good way of seeing that is the following. Assume you've got your edge. Take two strings, one with length R1, the other one with length R2. Place the first one with length R1 on top of vertex V1, only the end point, and try to pull it tight towards the other edge. So when you do this, when you stretch it or when you pull it tight towards the other vertex, it will cover either the entire edge or perhaps a portion of the edge. Okay? So this is what we're doing. If you just happen to have this one, when I pull the first string tight towards V2 with one end attached here, it will go as far as some point here, and because it's pulled tight, the length will be R1. You do the same thing for the other one. You attach one end of it here, and you pull it as much as you can tight towards V1. It will go somewhere here, R2. So in this example, the strings don't meet. Okay? And it's quite obvious that the length of this one and the length of other one is actually less than the actual length of the edge, which is the distance between V1 and V2. If they do meet, then you have any point at the point of the intersection of the two strings will actually do the job. So that's a good way of visualizing these things. So it's more general case with a tree. Again, these are the vertices with the same old edge lengths that I had before. And suppose R1 happens to be 7, R2, well, let's not take R2. Yeah, okay, let's take R2 to be 8. Okay, so in this case, this is a length of 1, this is a length of 1. Relative to vertices V1 and V2, when you have that string pulled tight towards the other one, actually it reaches all the way. And the other one also reaches all the way. So actually all points in between on the line, on the path connecting the two vertices will be okay for that particular pair of distance constraints, right? These will be okay for that choice of radii. How about the pair? For example, there's another one here, distance xv4. And let's take, for example, R3 to be, R4 to be 5. I don't know if that's going to work or not, okay? All right. So when you look at this one, you can go as much as 5 units, which takes you up to here, if I remember correctly, okay? Now, this string attached at vertex V1 will take you, that's 1 plus 3 is 4, it will take you up to here, right? I'm pulling it tight towards V4 along the path connecting V1 and V4. That's what I'm doing. So here you have no connection or no intersection, which means that even though these are okay, this one and that one will be not okay. Okay? So you want that situation. You want the situation of having the two strings, one attached at one vertex, the other one attached at the other vertex, when they are pulled tight towards one another, along the shortest path, actually, along the unique path. You want those two strings to meet for every pair. You want this to be true for every pair of vertices. There's no minimum maximum here. What do you mean? What did you mean? Because Ri are whatever they are. They are. No, I'm not worrying about that. Don't make the problem complicated. It should hold true for every vertex. In other words, every vertex pair. I don't care about the minimums, maximums here. If there's a single vertex pair, such as V1 and V4, where they don't meet, there's no feasible solution. These Ri's are not good enough to admit a feasible solution to the distance constraints. Okay? Don't worry about, secondary things, which is making things efficient. Don't worry about making things efficient until you first work out the correct thing, and after that you make it efficient. Okay. So in general, we've got the following theorem. The distance constraints with upper bounds of Ri's are consistent, meaning that they admit at least one feasible solution on the tree if and only if. What is the condition? Just from that discussion. The distance between any pair of vertices Vi and Vj should be less than or equal the sum of the radii associated with those vertices. This should be true for every I, j pair. You might want to include I equals j or not. It depends. If you already assumed, which we did, that the Ri are non-negative numbers, you don't need that equality here, okay? Because when I equals j, this simply says that distance between Vi and Vj, when I equals j is 0, it simply says that 2 times Ri will be greater or equal 0, or Ri will be greater or equal 0. If you already assumed Ri's are non-negative, there's no need for that. But if you did not make that assumption, you would want to you will want to include that, because then in that case that will enforce Ri's to be non-negative actually. Okay? All right. So did I make that assumption? Non-negative numbers. So let's not worry about that, but that will come in later when you start working with the z values. Okay? So that's why I wanted to mention that. All right. So what we want to do is we want to prove this. Which part of the proof is easier? This is an if and only if, so it's both necessary and sufficient. One is easier, the other one is a bit more difficult, or maybe considerably more difficult. I don't know. Which one? This one? Like this?
Yes.
Sufficiency is easier. So assume that this is true, then it should be there should be a feasible solution, or that these are consistent. You think so? How many people say the other one is easier? How many people say Ataberk's choice is easier? How many people say I can't see it? Huh? Okay. Okay, let me put it this way. One part applies to general networks, the other one does not. So in one of them, you're not using any property of tree networks, but in the other one, you have to use the properties of tree networks. Which one uses the general network properties rather than the special tree network properties in your judgment? The other one. Which, so this one. Okay, so let's just prove that one by assumption. What do we assume? There's a feasible solution X in the network, because I already said that it's true for general networks. So rather than tree network, let's just take it as a general network. Assume there's a feasible solution X in the network such that distance X Vi less or equal Ri, I between 1 to n. So what do I do now? Then for any pair ij with ij satisfying these, we have so for the particular pair I and j, you have two constraints which both hold at that point x. Okay? When you add them up, what do you get? You get distance xvi plus distance xvj is less than or equal to ri plus rj. Left sides added up, right sides added up. So you've got that. And, of course, this is what you've got. But also you have distance between Vi and Vj less or equal that one because of the triangle inequality, which is true for general networks as well, okay? Not for tree networks only. So this part is done. The other part is more difficult. How much time do we have? Only 2 minutes? 1 minute? Huh? 2 minutes. I can't do it in 2 minutes. Okay, let's just stop here. I'm going to pick it up on Monday. But by Monday, you might want to work out a proof for yourself at home. That's an exercise, food for thought for you. Okay? You have to use the special structure of tree networks, otherwise, you're making something wrong probably. Okay? You're doing something wrong. Okay, great.